dynamic of the population. So, when you model that, you have to make your model. Okay, so maybe you forgot to say, so you know that this famous sentence saying all models are wrong, but some are useful. Okay, so you make, when you do your own model, so you see the many projects. For some people, you have a model in the literature. Sometimes it's not so good. So sometimes it's the choice of the author to make this choice. You in your project, maybe you will make another choice. So it depends on your own choice. Okay, so what we have seen last week is, so for example, the lecture on Bangladesh was talking about cell, protein, drugs, and she was looking at the concentration of it, or the expression of some protein. So you can consider the population as a whole. Okay, so you make no distinction, or you can make some compartment. And you look, for example, the time evolution of all population. So you make no difference between the protein of the same species point. And you have the R. So if you remember also, Nakhon showed us some image. So you have the expression of the protein, and then so in the simulation she showed you with respect to that, and you have one image of MRI at level 1. But it depends where you take when you measure the expression. It depends also on space. Okay? This is one. So you look the population as a whole, or according to its characteristics. So its characteristic is what defines the population. So course of time, something, but maybe the most common one that everybody can understand is the age. So we have different age. We have different behavior, different response to the drug, for example. So age is one important characteristic. So let's see second one, maybe the space. Where you are is something very important. Evolution. So one type of evolution, you have to think your stage of evolution. Okay? So for example, the seed is not a tree. So seed evolve, become a tree. Okay, so evolution, so one important thing, so evolution and age are not time. Okay, sometimes you make confusion. Of course, you getting older with time. But time is the third age is your age. Okay? So age and time are two different things. Okay? Like evolution, so it will evolve with time, but the evolution is not time. Okay, so size for us, etc. Okay. So sometimes it's not so easy to know what the most important characteristic of the population. It depends on what you want to study, it depends on your initial problem. So we'll see some examples. So sometimes you don't need to just make something quantitative. You just want to know the number of people who will have a good response to some drug. Okay, you don't need to know all of this you need to know the age or maybe that what they like the way of digging, many benefits. So if you have important characteristics to take into account in your model, time is not enough anymore. So, wait. Okay, so the outline of Pathom, very interesting. So first I will talk about space to further that. So it's good for me. We have some songs that sweet. So that's space to further. So we have seen the last version. So maybe some of you already know what's the last version. But maybe you don't know why you can put the Laplacian in the model describing the evolution of the protein, or should say the dynamic of the protein, where it's come from. Okay. So and then I will talk about edge structure. So how we take into account the edge in the model. So we see different types of model for this, so it depends how we want to describe the edge. So you will see it's very different from the space. So the way you put the space in the model is totally different from the way you put the space. Okay, so what I will show you these few days, and so the last one will be on size of the current model. So because we have seen last week, for example, the size of the cell is very important when you have to apply drawings. So because of the size of the tumor. So you will see it's quite different. So there is no universal way to make super model. So I cannot say so. Even if my study is super model, it's not a universal way to build any type of structural model. For example, evolution, so I will not have time to talk about evolution, so a different way to model that. Different example. So you, even if you will see, so size and edge are not so far. So depending also the way you choose to model the size of the edge. So there is one way very similar to the edge and size, and there is another way totally different, which is the mass action law that's also right. Okay, so I will try to talk about this twisting. So of course I will probably have no time like all the theoretical part of the thing, but I will give you reference. So I think for all lectures you will have also the reference for everything, but I will give you at least the key to do it by yourself. After the okay, so let's start with the space triangle. The first one. So you see the one remark. So you see the CIMPA school is a Soviet industry. To see different way of teaching. So you see we have different professors coming from different universities, different backgrounds, and we all have our own way of teaching. So maybe this one is more traditional one, like we do in France, like in the paper 1.1, section 1, section 1.1. So some are very different. So it's also very interesting, and also you have also to manage a lot of different accents. Okay, more French accent, so that's a big kind of accent. After that, you have speak very well English. So you have to manage a lot of accents. So this is also a very nice way to learn how people are teaching. So enjoying is not there, but talking is also totally different style. Almost half of the lifetime. Okay, Okay, so let's start with one model. So I will start with what we call the meta population. Okay, so normally on Friday we have a presentation of one group. We'll talk about meta population, but you just organize them. You can see them in your place, you just organize them. What you do. Thank you. So the meta population. Okay, so the meta population is the concept coming from ecology. So what is a meta population? So it is a group. What is it important that spatially separated? I think I will. So, spatially separated population. What is very important also in the definition, they are from the same species. Okay? And the other thing is there exists interaction between them. Okay, if it's just a group of population living at different places without any interaction, it is several population. Okay, a meta-population is the same species, same population of cell, of protein, of human people, same species living in different places with exchange between them. Okay, this is a meta-population. So when you have two kinds of meta population, so sometimes we say 4 types or 5 types, but they all derive from these 2 types. So the rest is only extension of. So meta population, you find this in ecology, more in ecology, but it has been adapted to everything. Okay. So the first model, first type of model, let's start with, yeah, I thought, we have enough, yeah. So the first model is what we call the model island, mainland, or sometimes island continent. Or we use all the world. So you have to fix it like that. So you have the mainland, the big, and you have some island. So if I do that, these are population, not meta population. So to make a meta population, we need to have a chance of these people are traveling between the islands and the land. Okay? So this is the first type of meta population, or you can imagine a big city with a lot of population. And one city where people are coming from purpose to work and then they speak in the kind of. So this, all of these models of the interpretation, so it's almost in the same style, so it's called Markup 69, 67. So what you want to compute is the population living not in the continent, so because in this model it's a continent full of people, we want to compute the people who are living in the island. So what is in the model? So we compute P. So P the number so it's not the number actually, but the fraction or proportion, fraction of the so P of T at time. So in the model, what I say, so as I said before, we assume so the population of the mainland is constant. Okay, so and then to compute the number of population, and also detail what I say. So you see, we find again model that we are seeing in our content. So I write first the words, and then write the equation. What we just say. So you look the variation of occupied habitat. So with respect to that. So this I translate to equation is just the derivative of P, so P prime is equal so maybe just integration. So you are looking only on the occupied side, but you look people who are going in the island. So I minus what when for the expansion. So what does it mean the integration? So I will write the equation. So it means what? It means the population. So to go to the island, they have to find some place unoccupied. Okay? So if P is the fraction of the occupied side, so 1 minus P is the unoccupied. Okay, so let's just say that in top, why you have base point. So minus of the extension, put something simple, minus. Okay, so extension means in the model, a simple model, extension, either you are there or you leave the item. Simple, put everything. Okay, you see it's simple in the you can solve, and it's not so. So the second type of model is now what we call the model island, or sometimes we call it patch. Okay, so this one is really more used today. Still, there is 69, so you have a lot of paper from ski. So you have really paper on that typically tolerant. So what is the difference? Now, so you don't have any more a continent or a mainland with coastal population. You have only island, and you have exchange between all of them. Okay, so imagine, so I remove the main arm, exchange. So again, see, if I don't put any exchange, there are population. So now I put, for example, exchange, one, but so when you do exactly the same kind of thing, but it would be a little bit different. So the model now is written like that, or we want actually the model get some time. So alpha is not the gross negative, but the same, the immigration rate. U is not the mortality rate, extension rate. But it's more or less the same, so we have to take into account the file, but you will see it. So, and what they take also into account is the file. Sorry, and still the extension. So maybe it looks more familiar to you. So we write the other way, be even more familiar. So I can write this like this, or U T multiplied by 1 Okay, so you see this is a logistic equation. So we have seen also last week, so the logistic equation is the S curve or sigmoid curve. So what does it mean? It means the population in all islands will converge, so in some condition of the parameter, to the carrying capacity. Okay, this is quite normal, what we think. So you have place everywhere, and you want to occupy all the place, but you cannot exceed the maximum habitat. So you can solve the differential equation, or not again, but this is totally logistic equation. What you get. So just to see that the model is not so far from the reality. So if you look for the positive equilibrium, the positive equilibrium. So again, I remind you of find equilibrium. This equal to 0. So you have two possibilities. P equals 0, but I'm not interested in the extension. I want to occupy the site, and the other possibility is this one equal to 0. Okay, so what does it mean? P will be equal to the inverse of that. So P is equal to the carrying capacity. So the positive equilibrium is after simplification is 1 minus 2. Okay, so this is the inverse of this one, and then you can simplify the function. So we have 1 minus 2. Okay, so this equilibrium So it's positive, so exists and will be stable if so we have a condition of the immigration and the mortality, but it should be so if alpha is greater than. So what does it mean? So if I come back to my problem, so it means that the immigration is greater than the which looks natural. If the extension is greater than the immigration, you will compare to zero. There's more extension, so more people will die or will live. So if the immigration is greater than the extension, you converge the capacity, maximum capacity. So you will see minus, so usually, so the immigration depends on the distance between the islands. So it's usually inversely proportional to the distance. So the farther you are, more complicated it is to reach the place. So for example, this year, you organize CIMPA Pathom. So to reach Pathom, easy. 2 years ago it was one. More complicated. Okay, so if you are very far, immigration is complicated, and usually the extension depends on the surface you have to live. So if you are very comfortable, you want to stay. If you live in a very small place, you are not very comfortable, you want to. Okay, this condition means maybe the farthest is the place, the more comfortable you have to be. Okay, so if someone wants to go very far, you say, okay, but I need a lot of money. Okay, this is what does it mean. Okay, but what you have seen there, I'm computing the occupancy, but I don't know actually where are my people. Okay, I just compute the total occupancy, but I don't know if already all of them are here and this one are empty, or they are equally distributed. You don't know that with this kind of model. So this model are called implicit implicit spatial or spatialism. Okay, so if you go here, what are the people? So in the first step, usually you have this new information and you know. Okay, so what I want to do now is to explicit all of that. So if I know where are my islands, where is my continent, or are they, I can try to compute exactly the same thing, but in each place. And so if I compute the probability of each place, what I need to know is all these arrows. So I need to know how many people are moving from this place to this place, how many are moving from this place to this place, this place. Okay? So this is what we are trying to do now. So if you want to explicit the space, okay, again, here it's implicit because I don't know, so I know the number of inhabitants, but I don't know where they are. Okay, so I talk about space without space. So now I want to know exactly where they are. Okay, so to explicit the space, so what we consider now is not just P, but I will write P, I, P. So exactly the same, but the fraction of occupied that. It's okay, you can see that. Okay, the computer. When the same sentence are occupied like that. But in the island or in the patch. And so what I did more, so I did one thing. So here we talk about island, historical ecology, but you can imagine the space in the body, you can imagine any kind of space. What I need to know, what I said, okay, is I need to know all this area. So if I remember well all those cities, I think there's some people who were studying graph theory. I think so. So here, what we are trying to do is to include the graph of the population. And what I need after that, we call it G. So sometimes we call it omega plus G minus. So G is what we call the connectivity matrix. So define how we define this matrix. So exactly what I said before is the number of individuals who are moving from one place to another. So define by the coefficient of the matrix G at G. So it is the proportion individuals, the graph individuals, the largest, and the appropriate cell. So moving from the batch I to the batch. Okay, so sometimes we note like that. So if you are afraid to make a mistake, you can write G, I, go to G. Okay, so this is a connectivity solution. I think if you are studying math, somewhere in your background you add one lecture in graph theory. So you learn about connectivity matrix. Or if you don't learn about that, so it's a matrix with number inside. So then I can rewrite exactly the same what becomes the model, or for example like or advance or in each island I will compute the equation. Sorry, take this one. So it's almost the same. So I will write the same in a different way in each batch. So it means I have n differential equation. So it's simple, I have just one equation. So if you have 2 or 3 islands, it's not a big deal. If you want to compute Philippines is 7,000 islands, they say. So you have 7,000 equations. So maybe I can show you because we did that. We did this kind of thing for the Philippines, but not the 7,000 islands. So we take the main airport of the country. So I will talk about that thing. So when I present something. Okay, but anyway, so it means, so you will complexify your model, so it's OD, so it's not so complicated to model. model, but you still have to make the first choice. Okay, 7,900 is too much. So maybe you can select only the place where you have an airport. Oh, okay, so as before, so we have the immigration. So we detail a little bit more what is the extension. So you have immigration, okay, before one. Living place plus minus the birth minus okay, and then we can so birth and death, so just to simplify the thing. So in each place you have different birth rate, For just for today, and something simple for the birth, you can imagine what you want. So what is important is how you compute the integration. So maybe I can make a imagine I am I, G. So people from I are moving to G. So I'm moving with G, I. Okay, so this one is the immigration. So the immigration, right? So people who are our path going inside the east. Okay, so immigration first will be. So you are looking for people who have the path G coming inside E, right? Proportional. Okay, but I have to make it for all the islands. So I will take the sun from E from 1. Okay, so this is the immigration. And then the immigration is the people who are in I and leaving the island. So they are leaving so minus. So you are in I. So that's why sometimes say nice. So what do you want is I equal to G, and this is the people who are in. Okay, in the same, they can move everywhere, all the islands. Again, I have to take the sun. Okay, you see. So if you go step by step, it's not so okay. So it means you have to go immigration, you are here, and you can go in all diagram, and at the same time immigration, all the your place you are going in your island. Okay, so like that you have a system of differential equation, which can be very large. That you have. Okay, so now it's explicit. It's explicit because now I know the number of people who are living in each place. Okay, so the most maybe the most famous, the most common utilization of this kind of model is for propagation of epidemics in the world. For COVID, flu, influenza. So it's mostly the same guy who make all the simulation for everybody in the world. So it's the SIR model. So we have talked last week about the SIR. So susceptible to become infected and then they are retired or removed. So removed is dead or recovered. Okay, but if you want to make a SIR data population model, or find the curve between ICT how we model that. So usually when there is a big epidemic, someone will do the computation, so we make the computation mainly between the most the biggest airport in the world, and use this kind of so how you write the equation? So you do exactly like this side of the one. But maybe what does it do? So maybe I have so if I am in the city I, on this city I have my model S I. Okay, I have my compartmental model. Okay, you remember compartmental model? For example, so last week. And you have another place, and in this place you also have an SIR. Okay, this is one, another. Okay, and then you imagine so people can travel between this place. So usually R is a bit useless, but susceptible they can travel. So the susceptible they will travel and they arrive here. So if you are susceptible in patch P, I will become susceptible in this patch. Okay. Here I have D I. So susceptible they can travel. So there. But imagine you are in the beginning of the epidemic. There is no lockdown, nothing, so everybody can travel. So infected will also travel. For the infected people, also real. They also travel. Yeah. Infected here, also travel. Okay. So then you write your equation. So you do exactly as you do for just one place. Okay, so you write the sense of 4 pi between and so first I will so if you remember I will take the simplest SIR. Okay, so susceptible, so you become infected with a susceptible that some space. So if a susceptible is in contact with an infected. So with some infection rate, infected people are the susceptible who are infected plus delta X. And so since we take SIR, so you have the recovery rate, say you have R. So this is the standard SIR model. Okay, susceptible people infected when S is in contact with I, beta is the infection rate. Okay, but this one is if you don't put any, so then I have to do this for all places. Okay, so usually so beta is related with the virus. So usually beta does not depend on where you are. If it is the same virus, so beta is relation with the virus, so it does not depend on phase. Of course, then you can have mutants, so it will depend on phase or depend on the evolution. But I say I will not talk about the evolution. But the recovery depends on where you live. Especially if you are looking in the world, or in some place there are more facilities than another place, or recovery depends. Okay, so this is just the equation, and then I have to take into account all the trouble. So the trouble, susceptible or something, but write exactly the same equation. Before, so the susceptible from our place, vector, city, and susceptible minus the one who are leaving the place. Okay, exactly the same as before. And here the same, let's say we were at the beginning of COVID, so no test, nothing, everybody travel. Yeah. So even the infected one will travel. Okay, so then you can write on the equation. So Thursday we try to do that. So it's not if you have, let's say 3, 4, 10 days, don't so complicated, right? Imagine if you have to make the simulation for the world, a little bit more complicated, right? But actually it's not so complicated. What is complicated is to know G. So G officially does not exist, especially for this. But especially in Europe, it doesn't exist. So what is G? So GI. So it's the number of individuals. So moving from the I, the city I, G divided by the number of individuals in I, so multiply, so by some unit of I. Per day, per month. Okay, so each time we go to the airport, so the company was supposed to destroy your data, but actually the data is used for example, for this. Okay, all the people who are traveling from Pathom to all the places you have to perform, divided by the number of people in the BK. So officially doesn't exist, but it exists. But it's very difficult, so let's say for the common human being, so if you write to BKK airport, say, okay, I have access to this data, I am a young PhD student, I need to make my consultation, so you say, which kind of data? You don't have this kind of data, it doesn't exist. Okay, but so to get G something complicated. So this kind of method we use that for the Philippine economy. So a little bit more complicated. But what we have done, that we don't understand data, but we take the main city of the main airport of the country and make this kind of yes.
Could you explain what is the physical meaning of the red part and the black part? I mean, intuitively speaking.
Physical meaning of the red part. So it's this one means the susceptible people who are traveling, for example, who are traveling from some place and arriving in Nakhon. These are these people. Okay, this one is the susceptible people who are living Nakhon. Okay? And in the same, the infected people, you arrive at the airport. So normally when you arrive at the airport, if you remember, you have to declare yourself. Remember, you have a list of countries you have to declare. But these people who are infected who arrive. And this one is the infected who are leaving the place. Okay? So, but you can imagine, so during COVID, for example, the infected one didn't travel. But in COVID, you have more steps. You have the exposed one, for example. So, exposed means you are infected, but you don't know. So, since you don't know, you think you are in good health and you will travel, but you are actually infected. Okay, so in the very first model of COVID, we say, okay, you are infected, you don't leave the place, but they still propagate. So it's because also here we have only one type of infected people. For example, in COVID, you have people infected but without symptoms. So if you have no symptoms, you think you can travel, so you will travel. Okay, so you can multiply this by, you can complexify all of this. So writing the equation itself is not so complicated, but get the productivity matrix is more complicated. So I choose the real one. So there is mathematical method to try to simulate realistic connectivity matrix. So how you can connect individuals. So I don't know, maybe one group will show you some image of what type of matrix we are using to make the simulation. If you don't have any data on that, there is still some example. So it's coming from graph theory, how you can build this connectivity matrix. So, but it's still not an easy task, especially if you want to look up more complicated, not only individual moving. Okay, for just one example. Okay, you see just the way we start. So first we start with implicit method. Okay, you just compute how many people are in there. But now it's explicit, but more complicated. So the next step is okay, so how you can make it when you have 7,000 islands? Imagine. So and you don't want to write the 7,000 equation. So because you also have to figure back. So here, okay, so beta does not depend on I, so just one parameter. But then you have the gamma. Gamma depends on the beta. So you multiply. So if you know G, but if you don't know this parameter, you multiply this parameter by all the bits. So you have seen last week, so at the bench, we got maximum 20 parameters, it was already complicated. So if you have 7,000 parameters, actually it doesn't mean anything. So for example, in COVID, we have seen many papers like that. So people wanted to do the best model, but with 200 parameters. 1,000 pounds. Yeah, of course, it doesn't matter, looks very nice. But you cannot measure anything of your model. So you cannot find the parameter, so it's totally useless. But still, it looks nice. So you have to be careful on that, of the capacity of the model to find the thing. And especially if you are working on biological field, where the parameter, the data is reduced, so after Pathom, we talk about big data, so if you have enough data, it's okay. But still, 7,000 parameters in the model is totally not very good to be okay. So how you can do it when the number of patch is going to 15, or so another way of thinking is when the number of individuals become very large. So you have to change a little bit your mind. So you don't think anymore like that, okay, I will describe one by one. I have to change a little bit the way of thinking. And when you change the way of thinking, you change also the mathematics. Okay? So you see also this is one interesting thing. So when you are doing modeling, so when you start to study the model, probably you don't know what is the best type of model you need for this particular medical problem. Okay, if this case of the medical doctor, you come with one problem, okay, at least what you think about the model. So usually what you will do, you will start with what you know as a mathematician. Okay, you know ODE, you try to do, you know graph theory, you try to do graph theory. You know probability, you try probability. But sometimes it's not the good way of thinking. So if you don't know anything about the biology, so that's why we say also that thing. So you have a lot of biological terms, medical terms. So because it's important for you as a mathematician to try to understand the biological problem. So because it will help you a lot when you will derive your model. And also if you are doing only data analysis, it's also important for you to understand your data. Okay, you have seen in every project, so we choose things from medical or biological things, sometimes it's very complicated to work. And also you have to imagine, so if you work with, especially with medical doctor, so they have no time to study mathematics. So you have to make the effort to learn medicine and biology. Okay, but something has to do with saving life every day. So we cannot take time to do that. Better usually, let's say, simpler for a mathematician to learn biology than for biologists to learn mathematics. I don't say it's not possible, it's possible, but usually, okay, but deal with the patient, with the hospital things, so they cannot take time for fun. So, the way to model, especially thing is to use what we call reaction theory. Okay, if you remember, let's see, yeah, so Raymond is there. So Raymond, he has this attachment, he makes computation. So this is the difference. But where it comes from? So mainly we come from, okay, you have any patch, a smaller patch, and when the number of patches is going to infinity, what you do? So we start with this discrete model, so that I do not use this discrete model, I will use the probabilistic way to describe the norm. Okay, so let's consider a cell or particle. Cell. Okay. So you consider the cell that moves. So I will make a short. So randomly, so we will space step. So the space step is called delta x, it's not just I plus 1 like in the software. So you can move, and the particle moves at each time. Each time step, okay, so I'll do it in 1D because 2D, 3D is much more complicated. But it's very important to know, so at the end I will get a differential equation. But it's very important to understand where the differential equation comes from. Okay, so what does it mean? So 1D, so you think like that, so you have, right, so you have a particle, so you discretize your domain, so this is delta x, okay, or theory. So imagine you have your cell is there, okay, and then you can move randomly, so you can move to the right, we will set x, or change the color, or you can move to the left, here, or you can move to the left. With data. Okay? So the question is, for example, how to reach this point. Okay, you want yourself a right position. This point I will call it N. Okay, so you have many ways to reach this point. So if you are lucky, you go right, up. But it's random, you can go right, then left, then right, left. Or you can go left, and come back right. So it's a random process. Okay? So what you compute, so what you are looking for is the probability to reach this point after, for example, 10 steps, 12 steps. Okay? Exactly what you want to compute. So I will write this, so E, and so the probability to reach this point and X after and delta T time. Okay, so imagine I give n equal 10. What is the probability to reach this point after just 10 steps? Okay, so this kind of model can be used also here. So I was imagining when I was thinking about humans, so when humans are moving from one place to another, so I hope it's not totally wrong. Okay, when you travel, you buy your ticket, so you want to travel, so it's not a random process. But if you are looking for a set, so you can make this kind of thing, but instead of having a collective image matrix, you will change that by a random process. Okay, so it becomes what we call Markov chain, for example. So I don't have no time to explain more in detail the probability, the stochastic problem. But it can, oh no, talk a little bit about that. Okay, so what does it mean? So just simplify. So to reach this point, so we write so it depends. So if you are very familiar with the probability, you can already compute this probability. Do you recognize what is the law for that? No, not yet. No, you see, actually it's not complicated. So if you remember your class probability, so you have, so maybe you do with the coin. So you have a coin, and you have two choices for the coin. So this means you have a binomial law. Remember binomial law? So you have one probability and two choices. So this is what I will run. So let us do this. So we run A, so number of steps to the right. B, the number of steps to the left. Okay, so you can A to the right and B to the left. Okay, so what does it mean for N? B. So don't wait. So we have done the law. We rewrite the probability. So the probability I will do is the number of possible passwords divided by the total number of passwords. So what does it mean? So in N, so N is the number of steps. So it's A plus make A to the right plus B to the left. It ends the total number of steps and the opposite to A minus Okay, I will do this case. So imagine n is on the right and do your close equation. Or if you first take n plus n 2 b n. So then the probability you can copy the probability, so b and so with the number possible or sometimes we say feasible pathway so to reach this point, okay, divide it. Total number pathway with the n. So the possible pathway, so if you know the pathway, so it is the combination. Yes. Combination A to the right, A step to the right from n possible way. The number, the total number, so you have on step you have two positive, right, left and right, so dividing to prepare. So the combination, so this is the possible way dividing. Or if you don't see very well, I can write this and A 1R for L 1 minus R. Write it together again. Right hand. A. Okay, so you recognize the value now. So what does it mean? It means E, this probability E follow binomial law and probability. Okay, so here there is no trick. I'm saying that the same probability to go to the right and to the left. Okay, one part to the right, one part to the left. Okay. So and then now, so the question is what happens over n goes to b. I think I will have time to introduce the question. What happens? And go to. Okay, so just one remark in terms of modeling. So when you say n goes to infinity, so you don't have to think the number of steps goes to infinity. You have to think the number of particles that are moving goes to infinity. Okay, so it's a different way of thinking. So even in terms of analytics, it doesn't change it. But what I will do is not making the time going to infinity. I'm making the number of cells going to infinity. Okay, each cell move. So you multiply for n, so you have to think n as the number of cells, okay, not the number of cells. Okay, so imagine now you have lot of cells, lot of gas, water. Okay, so we need to simplify this formula. So what you want to compute is the limit when n goes to infinity of n. But a depends also on n. So you have, I will remind you what it is. Okay? So you have n here, n here. So you remember Stirling formula? So we use the Stirling formula, which is the factor of n. So it's equivalent, so when n goes to infinity, the square root of 2p and the exponential and log n minus n. Okay. And so you do it for the probability. So what we have, the probability and so we just find 1. So the denominator coefficient is n factorial, a factorial, n minus a factorial, and multiply by 1. Okay. So then you replace this by this formula, this with a by the same formula, so go 2pa exponential of a log a minus a, set for n minus a, so this one, so 2p parenthesis n minus a, etc. So it not right, but at the end, so we write this, what you get after substitution, 2 value in n and exponential minus m squared divided by okay. So what we get at the end, the exponential of minus x squared. So this is the Gaussian function. Okay, and so if you remember in your class, or maybe you never make the proof, but at least with the computer, so you remember that the binomial law converges to the, what is the name of this law? The normal law. No? Yeah. So if you remember your class, sometimes you do that even in high school. So you make your test of your binomial law, then you increase the number of tests, and then at the end you have the curve. You have seen this kind of simulation. It's calculated with Excel, not so. So the binomial law converges to the normal law. Curve. But it's based on the scaling form. So at the end I have this thing, but still doesn't look like the ladder. I look far, but it's not so far. We are close. Very close to the differential equation. Okay, so I will come back so to have the equation, so I need to come back to the bit, so I have n, I have delta x, so this guy I will give it a name, I will call it x, and then t I will give the name, I will call it t, so like that I have the position x, the time t, so if I just change a little bit my notation, so I write x and x and t and t, So if you want, what does it mean? So n is x over x is n t over t. So what I have is n, so I have the probability x delta x t. So it's just a normalization, so you divide by 2 delta x. It's just to make it a little bit nicer. So it's equivalent, so when delta t and delta x go to 0, so it's either t. So I have delta t over 2 t delta x squared times exponential of minus x squared 2 delta t, and here I have delta t. So it's t. Okay, so and then one important condition. So if the limit when delta t and delta x go to 0, so you see you have delta t and delta x squared. So if the limit, so delta x squared divided by all here. So if this limit exists, I'll give him a name, call it G, positive. So if this limit exists, so this is what we call the diffusion coefficient. So this limit can be easily written as, let's wait some time and turn it like that. I have no need to write. So what does it mean? As of the limit when delta t, delta x goes to 0, of this probability p is x t divided by 2 x. So it's x equal to 1 for dt, the square root times exponential minus okay, so this one I will give a name, so we try to create. So this is what we call the heat curve. Okay, so we start from the probability, make the particle go to infinity, and at the end, I obtain the Gaussian law. So, but still, let me write just that. So, what is the relation between this case and the Laplacian we are seeing many talk and lecture. So, this function, the function k, we write this plus xt, and also something positive. So please give exactly the function there. So this is what we call the fundamental solution. of what we call the heat equation. So what is the heat equation? So you take the derivative of this function k, the partial derivative respect to time. Okay, so time is here and time is here. Divide. Then you take the second derivative respect to x. So x is one there, so you have 2 times. And you will get, so for example, equal to 0. So but with some condition. So there's 2 conditions. Yeah. So we need the initial condition, so k at time 0 is equal to 0. So here, because you have to be careful, so divide by 0, and take the limit. So when I say equal to 0, it's the limit when t goes to 0 is 0. And last condition I put there, so the integral k x is equal to. Okay, so the proof is not complicated, so you have the formula, you just take the formula and try to compute it. So if you never did this computation, it's something interesting. So maybe someone remember how you compute the integral of the Gaussian function? No? Don't remember? So you write it in 2D. Forget that, so you have the expression of minus x squared minus y squared. So you take the double integral, then you write the polar coordinate, and in polar coordinate everything is simplified. You will obtain p multiplied, so you will obtain this. And then it's okay, if you never did this, this is a good work. So double integral. Exponential minus x squared. So it's polar coordinate. So very good exercise. If you never did that, it's important to have made this once it is like, then you write x r cos x r. You made a shadow. Okay. So this afternoon, so we change a little bit. So this afternoon I will teach again. So this afternoon we will see, so for the moment I have just this equation equal to 0 with this initial condition. What does it change if I have no 0 but then here also not 0? So how we can find the solution? You will see very easy. When you know k, you can solve the equation very easily. But what is very important to understand is the bonding. Why? So the second derivative of the Laplacian to d. Why it comes from? So you see my initial assumption was I have a particle that moves randomly following a binomial law. Okay, so if I'm looking for the density, so maybe I write later. So now I have the density of cell. Okay, when n goes to infinity, it means you move to the density of cell. It is given by the Laplacian, the equation. But by what is behind this, it means so each particle of your population move randomly following a binomial law. Okay, so this is very important. So you cannot just say, I will make a spatially explicit model using Gaussian diffusion by adding a Laplacian. Of course, if you are doing mathematics, why not? But if you are doing a modeling for medical thing, you need to be sure that what you are modeling is the description of the population that each particle moves randomly following a binomial law. Okay, so if it doesn't follow binomial law, it's not this equation again. So here is also it's true only one. So if you try to do it in 2D, so you have a square, and the particle can move in the square. More complicated. In 3D, more complicated. Imagine you have wall somewhere in my line, and then the second of the wall. It's more complicated. You can imagine many different things, but again, so when you want to do simple things, okay, you put l'attention, but you need to remember this assumption, okay. My particles are moving randomly following the wave. Okay, most of the people you will see l'attention, people they put l'attention like that. When you ask them why you put l'attention, we see with red marks. You can ask them now, why you put l'attention? Okay, so thank you to continue your lesson.